projects, and I will try to right away visit everyone one by one, and if there will be some common things interesting for everyone, I will join the stage and share it with everyone. So maybe I will start with Mai, because she's not coming here every time, so it will be reasonable, and then I will follow everyone here and then connect those online.
This is what I have so far.
No, where is MATLAB?
MATLAB?
Yes. It's okay. It's okay. It takes time to set up.
Okay.
So please run one of the codes and show me what is going on.
There's much going on with 156.
No, not here. Oh, okay. Oh, no, keep going. So what are the figures? Figures.
It will generate it.
Huh?
It will generate it.
Okay. Can I touch it? Okay, thank you. So it does press any key, right? You saw it before. And after you press, it generates the movie, right? So if you look here, you need to make sure this movie is recorded, right? So you remember it was taught in the labs, and if you don't remember, just look recordings or talk to anyone in the class.
Okay.
So then each time, well, no, it says 156. So you may want to scroll this number near the value 1 and near the value 2 and near the value 3, like run the code, I don't know, like 60 times. And then select those movies that look, well, I'm not telling exactly how many times, but show how much the difference in the movies, what do you see if you change this number?
So basically change the number, some close to 1 and some close to 2.
And maybe close to 3.
Maybe 3.
Yes. So try like 0.98, 0.99, 1.0, 1.01, and see what happens.
Okay.
And then just running and watching is cool, but how can you tell other people what do you see? So instead of just running for yourself, you need to add few lines that will make record a movie. And each time you run the code, you change the file name for the movie and then upload it to YouTube. And then maybe you select the best ones and show them during your presentation. Make sense?
So like make a movie for each node that I have.
Yes.
And then you choose ones then?
First, you save movies for each of them, but your time for your presentation is brief. You cannot show everything, right? So you'll show only those where you discover something interesting. Okay. And you see it, it takes quite a time. So you cannot do it in one day or one night. So you need to plan. If you see that you can run maybe 3 times or 4 times per day, then you need to do, it will not take much time to run. You run and then go do your things, but you need to like do a few minutes every day.
So how much of the loop is okay?
You set it up yourself.
Whichever one I want.
Well, if you set it too short, you will not see anything. Yeah. But this is probably more than enough. You can like maybe put 100 or 200. It will be enough. So loop goes until n tau, and you may set up this time like at least 200 instead of like. But try to be creative. You are expected to know how this code is working and just. So what you're expected to see is that right now there is like noise, right? Those red and green things, they're not very beautiful, right? If the number will be close to integer, like literally 1, literally 2, literally 3, there will be some pattern that you observe. And also the diameter of the circle will increase depending on this 1, 2, 3. So you want to like study and deliver what it is.
How the pattern goes.
Huh?
And see how the pattern is.
Please repeat.
The pattern, I mean.
Pattern, yes, yeah, thank you. And movies are the best.
Okay.
Movies are the best, but you also can try to make screenshots and put them into the report. So yeah, maybe we can stop because it goes too much. Let's see. We need to so this is a good command, and we need one more. It's probably task number 1 to convert this code into the format that will save movies. This command is for old version of MATLAB. It will not work. There are updated commands. And then you basically change this number.
Node.
Yeah, node, rerun, save movie, and then report the pattern.
Scroll down.
Which one? You keep it, select a number that you think is reasonable and keep it constant.
Okay.
This is enough. So you may start doing it right now, and I will make a full circle with everyone, and then I will visit you once again, and here during the lab we will talk more. So
put each of them in a movie, right?
Yes. So first learn which commands should be here. So this is old. It's something different. You need to learn commands for the movie. Okay.
I don't understand. What
Wait, did you watch all labs that were here recordings?
I do watch labs.
Did you watch so how to do movie?
Oh, you mean to?
Put here commands that will record whatever happens on the screen into format of a movie.
Oh, okay.
Make sense?
Yep, it does.
Okay. So please do it as a first task right now.
Okay.
And then after you do it, you just wave hand and I'll stop by.
All right.
Okay.
Yep.
Yeah. Thank you. Whew. I will be with you in a second. Joe, did you hear our discussion with Mai? Or here is no unmute. Joe, did you hear our discussion with Mai? Okay. Well, in your code, maybe you heard a little bit of it. In your code, you do have a variable for magnetic quantum number. It can be called just a lowercase letter m, or maybe the word nodes. And in the current version, likely it is set up for the value 2. And your task will be to rerun the code under different values of this parameter m. I'm just giving a brief hint, and then after I visit everyone in class, I'll stop by and chat with you with more details, and you'll share screen. Make sense? Okay, yeah, thank you.
I've kind of looked through what you sent me. It's helping a lot with making sense of what's going on. So when it goes linear, is that when it's completed the react?
Right. So this dashed line, it is interatomic distance. So x-axis is distance and y is time. And if we you have the code right here. We have regular USB. You can temporarily steal this one and stick it into your no?
Try. Okay.
Okay. Good. Yeah, and later we can also plug in your the display
Yeah.
and make it comfortable work
Computer
with.
still be slow though. It's not.
She's going to learn how to make movies.
She should look at my PowerPoint.
After we are done, you may help her send PowerPoint, but let's focus on your thing right now. HEM2 and HEM3 is higher quality. That's so it's more reading and dealing with code because it working. So Lisa and Samir. Samir is more recent. Yeah, he's a high schooler, and he came for 1 month.
Did you write all this?
No, he wrote.
He did.
But I have like several postdocs and grad students who are helping, and he's not looking forward to continue it with big dedication. So you can replace him with much better quality.
Can I though? It seems good quality for reading. I haven't read much on slides.
So, yep. What do you think of this equation?
Those are different states.
Right, but what is each symbol does it stand for?
Hamiltonian momentum potential is.
And it is something in direct notation, right?
Mm-hmm.
So it is written algebraically as a single line, right?
Mm-hmm.
So I'm just, it will be quicker. I'm going to draw something on the board, but it will be primarily for your project. Hello, how are you? How was the seminar? Did people ask him too many questions, so it was okay? When is your second year seminar due? Next year? But you know what you saw demonstration what to expect. I'm just lazy to write, but you see, so direct notation and matrix notation, right? So the Hamiltonian is composed of like 16 matrices, and if we need like maybe H from 0 to 3, it will be from 0 to 3 H03, but it includes all of them, right? And those on the diagonal, each of them does have kinetic energy. Therefore, we put it away, like we can remove kinetic here, and at the front put kinetic energy times identity operator. Make sense? Okay. If you want, I can write much more details.
Where is it in this?
So let's go. So kinetic energy is the same for each state. So you can always put here. No. Let's see. Maybe it will need signing in.
Let's see if it'll work. Might need to.
Okay, it does. It does. And then it's not many thoughts, but it's Control V.
Yep.
So put here 0, 1, 2, 3. So, but if we have all 4 basis states, then it's same as identity operator. And then there is a potential 0, 1, 2, 3, which is different for each state, right? And they feed by this Morse potential, which is you saw the figures, right? So it goes to infinity when distance is very short. It goes to 0 when distance is infinite and it has a little dip similar to harmonic near the equilibrium.
Is it in here?
Right. And there are parameters that show how much the dip is different from infinite value.
Okay.
And if you set it very small, then it looks almost like 1 over r, right? But we have different potentials, so depending on the electronic state, it's. And at the end of this write-up, there are values for this d I, beta I, x not I, and delta energy. So by a couple of parameters, we set up our potential surface. And what is next? So first line was all diagonal. Now here we have from 0 to 2, 2 to 0. I was miscounting numbers. It should be. So is do you recognize this mu times E? Let's ask Lola. Lola, what is mu times E? Uh-huh. Well, if the molecule is irradiated by light, by electromagnetic oscillating electric field, and if this is dipole, transition dipole, between state 0 and 2, what is the product of them? So dipole times electric field is energy. If they are oriented parallel, it is minimal. If they are against, it is maximal, right? So it's polarization. And how does light interact with matter? How does laser excites molecule?
Absorbing energy going to the excited states.
Yes, but through which mechanism? What's the energy of? Yes. What is the mechanism of? Yes, but absorption goes through dipole interaction. Energy of interacting between molecule and light is dipole term. Dipole times electric field, right? And if you take this dipole squared, it will be oscillator strength, right? So transition dipole, you have it in phi oscillator strength, and you have it in Gaussian output. So if you want to do it on a more basic level than this advanced graduate students do, then we just put the Hamiltonian energy of interaction. So dipole corresponding to transition between potential surface 0 and potential surface 2 times electric field. And it is included in this term. So when I cannot speak too long, I need to visit everyone, but I think it is more important than technical details. So when light is shining, then we can have transitions from ground state 0 to excited state 2, or oppositely, we can have transition from excited state 2 to excited state 0. And when you watch your movie, you saw initially it is in the ground potential, and then suddenly it promoted up. It's because of light promoted to the second state. This one, non-adiabatic. Let's go to your movie and replay it. Okay. Stop. So maybe we start initially when this one is promoted here, and then it goes down, right?
Yeah.
And then originally there is only green and black, and then you see there appears blue, right? And then we have, when this potential surfaces intersect, we have equal proportion between green and blue, and when they add together, they give this black. Right? So it is here non-adiabatic couplings makes state 2 to be promoted to state 3, or state 3 to promote it to state 2. So due to this coupling, we have this mixture.
Okay.
Okay, let's go back to the code. So the size CHEM 2000 by 2000, and if you do CHEM 3 2, it should be 500 by 500, right? So we put here 500, 500, 500, 500, so we can build this super matrix. And then this Hamiltonian enters into the super evolution operator. So now we need an initial condition.
That's what I was going to ask. How do I change the number of pulses? Because isn't that what you were saying? I should probably focus on how it changes.
Yes, it would be something novel. So if
Okay.
If you care only about grade and do not care about original research, you can just run and explain what you see. If you have ambitions to find novel, yes,
I see.
pulses is cool. So yeah, this is what we all should teach to my end. Maybe Hamidou will also ask about it, but keep. But you have MATLAB on your. Okay. Probably it will be good if you. I'll ask permission of Wyatt, but maybe you later on team with him and you will help each other. How many times? You know, like in fairy tales, you need to cast a spell 20 times and then magic happens. Do you have me? Yes. I will stop by after visiting with everyone, but you didn't hear, you was in the class today, right? So if ab initio is too challenging, you can just guess the positions of equilibrium, which automatically will change the reorganization energy, and then plot emission spectrum as function of equilibrium position of excited state. I think it will be the quickest thing to do in this project. Huh? I didn't want?
Yeah, you wanted me to do ab initio.
Yes, but we shouldn't load you with too many things, right? It should be something quick and simple.
I know, right? Don't worry, we're here.
Okay. So, Rabi. 1. Okay. And tau. Okay. So I will make some changes, and just in case they're stupid, I will call them stupid version or version S. So let's set up at the very beginning Rabi equals, let's say 2, but you can put 10 or whatever, and then n tau to make it maybe 140, or maybe let's do it this way. It will be really stupid.
Okay.
Ideally, one would meticulously read everything and make an impression, but we want to speed up a little bit. Now, where is the Where do we set up the file?
It has like 400 maybe.
Okay. No, it should be before this replace children. Replace children, it means it's already some graphical information. No? Maybe you were.
I just go.
Uh-huh. Yeah.
Sure.
Right. Or maybe
What was
open. Okay. Yeah, you are correct. So let's call it version S. And here, so two changes. The RABI was set to 20 instead of 1, and tau was substantially shorter, about 20 times shorter. So save. Just if you had any figures, we go here and then run. Probably you ask to push.
it's probably easy.
Okay. After we see how it runs, I need to visit others, but
I can email you if I have any.
and I don't know how busy I am during the Thanksgiving break, but I'm less busy, so you can set one-to-one meeting if needed. Press any key. Busy once again. Okay. So now it goes here. It repeats same thing. Oop, and then it jumps back here. Then see it already accumulated some energy and it tries to go for, then it jumps up, goes a little bit.
Why is it doing that?
And then jumps down. Because we apply a train of pulses. So before we applied just one pulse to excite, and then we have a train of pulses.
Okay.
You'll see what, I'll stop by what Joshua is doing. He's doing just 2 pulses as his main goal. And your original version of the code works for 1 pulse, but if you increase number of pulses, some additional mechanisms can appear. And after it ends, you'll see that this white stripe with dashed lines may look dramatically different.
Okay.
Okay?
Yeah. I'll play around.
Okay, super. Did you learn how to do movies?
Well, I tried, but then this should be the movie. It says this. Instead, I have so many things.
That's good. That's good. Do you have movie?
No.
No, you don't.
Well,
So
you know how this should be the movie. This one.
yeah, this one should be the movie.
But
What are you doing? You will not be able to run it from MATLAB. You need to upload to YouTube. Even on this computer, it may or may not work. Let's go to your Gmail account.
okay. Okay. YouTube.
Yes. Plus, let's create upload video. Select files. Then find this .avi file. 0 bytes. It's not good. the movie is not saved. You need to redo it. Oh,
This
here.
one. Yeah,
This,
it's
okay.
that one.
Yeah, open. Just scroll. You need to tell it is not for kids. Scroll, scroll. Otherwise, it will not learn. Let us go further. Just click selecting. Next. You can go next. It's fine.
I just want to rename it. Mode.
Okay. Next. 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 Public. Because you publish. Okay, now let's click and watch. So you see how it, what it does.
So I'll change the notes and see how. it goes.
Yes, exactly, exactly. I can briefly tell you what is. Let's go back to MATLAB. You've noticed that there are several images, right? Can I? Thank you.
It's a lot of them. Yeah.
Here.
Mhm.
Okay. Okay. One can manipulate either by clicking, which is a little longer, or in command line. So I don't like you can find how to do it, but there is a way to manipulate figures. Sorry. So this is, I think, result of diagonalization. So let's just operate this figure quickly. So your main goal is still just change parameter rerun, change parameter rerun. I'm just doing something in addition. Axis. So we want to look only on small fraction. You can maybe keep from 0 to 800 on X and then from 0 to 100 on Y. From 0, 800 to X, from 0 to 100 on Y. We may look even 10. So those are energies of eigenstates, and they become more and more sparse as energy increases. This is the typical feature for like how Hamiltonian, how energy of rotations depend on the energy of the magnetic quantum number. So they're becoming more and more sparse. But there could be a parameter for magnetic field, which it may be here, or we may add it later. But let's, if it is not yet here. Magnetic field is not yet here. So I think you better keep doing as we agreed, and I'll instruct if something else is needed. But right now you're on a good path, and it will be necessary minimum for the course. When you change the parameter nodes, you may change the name of the movie accordingly, right? And let's do something just as a demonstration. If you do 300,
Mhm.
300. Save as.
Mm.
Save and run. So wait, I want to then ask to. Oh, too far, too far. So you do not see it because the I need to stop. Control C. Let's do.
The node is on 200.
Yeah, let's do near 200. You'll be more interested. Okay. Save as. Save and run. Maybe you can. I just do it like it. It may put. Let's close all.
All the other figures.
Yes. Oh, it was here.
Mhm.
Yes, it was here. Okay, let's maybe run once again. Again, it probably plots in some other window. Yeah, it's helps you to just erase all of them and then. Five, four, close 3, and even close 1. And you'll be safer. Run. No, something is not good. See, clean. Just want to bring up the. So your first movie was correct, and now we need to have new image here in this on this image and saving into new movie. But something is going wrong. I need to help others, but I will stop by and
I
try
will
to.
change the numbers and save.
Thank you. Yeah, sorry, it took longer. I hope you'll be able to do a.
So you said in class, exactly, is this already in the code, the integral fitting rate? Or how do we implement that to do this?
Okay, I will show it on the blackboard, and then we'll identify if it is not in the code. I will send something from myself, or each of us should be able to program it. It's a really easy thing. Maybe I'm going to erase it. Hope it's not a problem. left, right, right of t. So let's, did any of you took kinetics or elements of kinetics in the past? Sybil? No? Kinetic, yes? So what is the reaction of first order?
First order reaction
Uh-huh.
minus ddt of c.
Okay. And what is the solution?
I can't remember it.
Minus d dt of c equals what?
Minus
Something like that, right? Zeroth order reaction. And then the solution c is something like exponential, right? Or if it is opposite thing, then it will be like if it is reactant, then concentration of product will be 1 minus e minus let's use letter k, kt. Make sense? Because reactant and product should be 1. So let's assume that we have this p as function of t, zeroth order reaction. So 1 minus e minus kt. Okay. So on one hand, we do have this theory that Hamidou taught us. On the other hand, we have MATLAB calculations, and we want to convert numerical data from MATLAB calculation into one constant. We can always make derivative, but derivative changes as we go through time, and it is not as reliable. If so, derivative changes, but still there is a constant of reaction. So what if we do the following trick? We take this equation, right, and integrate it. Integrate from 0 to infinity dt, from 0 to infinity dt. So on the left, we will have just, I will use capital P because I'm lazy to do these brackets for concentration. So P of t dt. And here we do have let's do better. Let's move 1 into here. So 1 minus p integral equals e minus kt. So I was not lying, right? Catch me if you can. I do mistakes sometimes, but hopefully not here. Now, what is the integral of exponential? It's exponential itself, right? So we have e minus kt, but we were able to do it only if the integration variable is the same, right? Minus kt divided by minus k. So we have minus k here, and we need to evaluate it at point 0 and at point infinity. Correct? So when upper limit is infinity, we have e minus infinity divided by constant minus e to the minus 0 divided by minus k. Right? Bless you, bless you, bless you. And then as a result, we have plus 1 over k. Right? So the k is the stuff that we need. And on the, it's on our right. And on the left, we had this integration of your numerical data. Right? So if we combine left and right, we can get that k equals 1 divided by integral from 0 to infinity 1 minus probability of product of t dt, right? So if you have numerical data for p, you're going to 1 minus this data, then make just summation over the whole trajectory, multiply by dt, which is variable tau, and then invert it, 1 divided by result, and it will be the rate. So this, I don't know if Adam is listening to us, but if your code doesn't have this trick implemented, you may try to implement it. It will substantially reduce the error, and the oscillations of your result as function of parameter will be much smaller. Okay, I'm done. I will go to talk personally to Wyatt. Wyatt, did it answer your question? Okay.
I have a different question.
Yes, please.
So when we did this, how did we define UU? Did we define it as VV? I don't remember.
I understand your question,
Okay,
but
I just put this here to remind me.
yeah, my speaking coprocessor is much slower than thinking coprocessor.
Because this is for plotting the eigenstates, right?
Exactly.
And
So
then-
it is my non-elegant bad programming that the letters VV here and there same variable for different things. But for the eigenstates, in addition to this line, there should be one line plus this. And I better type, and then we'll discuss. So if you type states energies equals eig, sorry, and put semicolon, otherwise it will be too much garbage information. So now the okay, what's the new figure? If I do mesh energies, it will be not very comfortable to analyze, right? But it looks like a diagonal matrix. If I do plot diagonal of energies, it's something we can look at. So if I want diagonal energies, or without diagonal, I can just do this way. Energies, and then put index, let's say 1, 1, which will be the first element. 1, minus 0.33. Make sense? It's the first one here.
Right.
Let's navigate, focus on from 0 to 20 and from minus 0.5 to 0. diagonal energies, comma, oh, once again. So those negative energies means they are bound states. Right now, if we repeat this little thing, as you, thank you for recording it. But
The N was,
n is fine, but we can set n equals 1. You can put here, what did I call it? States?
yeah, and then energy.
And probably we need to, you can set n equals 1. And after this, we can do it doesn't want to copy and paste.
Just move it to the other line, I guess.
Would you please copy paste? Oh.
Let's do that.
Oh, it is too smart. It doesn't want to put 2 commands per one. Okay, that's good. That's good. We temporarily remove this, and we
Right.
okay.
Yep.
So it is the ground state, state number 1.
And then
And if we
add this for the additionals, the states higher than the ground level.
And one can write a little add-on script, either as additional few lines or as a script that you run after main program is done, which will make like 10 lowest states and plot them nicely.
And then, okay. On the same, plot them on the same,
Yes, it will be.
but stack them.
If you put each of the line on a separate panel, it will garbage our book of reports. It will be hard to navigate through them. It's better to be compact.
Okay.
Make sense? Sorry, I didn't answer you in details to your email, but please send me a reminder. I want to send to you and to everyone the thing that I was distributed in printing this morning. I have them electronically.
Okay.
And there were some examples. There were several examples here similar to this one, not literal, but you can borrow something. And I need to visit it at least once, everyone, but then I can share or write in you this piece if needed, or do it next day.
Okay. Yeah, I might later. I might need just a little more talk to exactly how to like set up the different ones.
Okay.
And then for both of us, where would be the best spot to include that? Because so we define PR3 here. Would it be best to put a line in just right after that or further down?
Let's check if it is already defined. Wait. See, PR3 is already defined, right?
Right.
So what's the problem? What is the best value of x2?
What is the value of x2?
X2 is how we split our space on 2 segments, not necessarily equal. Is the borderline between reactant and product.
Right.
So if let's type in the command line x2, 100, and let's x open bracket n PTS uppercase n PTS lowercase close bracket. And NPTS. Okay, 200. So 100 is literally a half. Right? Can you alt tab to bring up the image? Alt tab to bring up the image. Well, in middle point will be 50, and for this many state, maybe the actual middle point will be not like middle point of your oligomer will be not a middle point of your cell.
Right.
So maybe it will be something like 80. So you
might have to adjust that.
Yes, yes.
Or the the
Mhm.
endpoints back to what would be 160.
If number of endpoints is 200, right?
Yep.
And we want to shift it. I would just approximately take it like 80 and see what happens. Or you can do proportionality calculation. If this is 200, this is half of it is 100, and we need to have equal number of things, then it will be like 40 will approximately correspond to how many.
Okay.
But it will change just a little details. Qualitatively, it will not affect things.
So the question, this PR is defined here
Yes.
already, and that's the P of T
Yes.
from up there.
Yes.
So for to finding the K of T and using that.
Let's try doing together. It will be, even if you are short in time, if it is not programmed, it should be after loop. We can later inspect this writing, but it's so much easier to just type in U. No secrets against you. I'm just, my hands are not so long. I'll then turn. So put PR3. No.
PR3 is
I just want
1 point.
why? Oh yes, yes. Thank you. Averaged PS3, right? Or something like. Yes. Good. See, it's anytime it makes inflection, it will add substantial error, and the rate will depend on how do you define. Now let's do 1 minus. Okay, and now you can do 1 minus times tau. Okay, and now we just do sum, and then we do 1 divide, and we can call it rate. So it will be in the units of inverse femtoseconds, not inverse atomic units. And atomic units are, and femtoseconds are factor 30, not 42. So, so if you want it in femtoseconds, I think one needs to I'm a little stupid in this conversion. So if time of transfer, I'm not sure, just computed it and recorded it across the time, and we'll fix the units after.
Okay.
And here is a thing for Sybil.
And then that just put in after the, somewhere after the loop, after the average is found,
Mhm.
or the base defined. And then last question. I think.
Yeah, go ahead. Go ahead. Go ahead.
Oh,
No, it's okay. That's okay.
for yield of reaction for P right and tau, do we use? Yes, do we use the maximum like single value?
Yes, yes.
Yes,
P,
okay.
PR3 of and tau, literally.
And then I think that's it for now.
Okay. Yeah,
Thank you.
Thank you.
Thank you.
Can I join you here? I'll stop later. I will start talking then to Joshua. Can you share your code with Hamidou and just so that he doesn't feel bored, let him run it?
Oh, okay.
Yes. So how things are going?
So far, so good.
Okay.
I just noticed that here is like almost somewhat similar to like there, but if I know there's pro, then maybe I should have a little dot that travels along this line.
Mm-hmm. Okay. So I have two questions. First question, like, do you have any questions yourself? And second question, did you select which parameter are you planning
Yeah,
to change?
I was thinking about the ensemble.
Number.
Yeah, the number.
Okay.
Yeah, I have been and just having. I mean, I have a lot of images, but I think the one problem I had though is that was the density matrix. I accidentally had a -1 instead of 1. So I mean, here, so I accidentally had it like this because I was just playing around. But then I just realized that, so I just made it 1 instead of -1 and just saved the images.
Okay. So which variable changes the number of elements in the ensemble? Okay, yeah. So you can just continuously scroll it and see how results change. Next question, were you able to create movies?
Movies, not yet.
Or you were not trying, or you
Well,
found
I
some
mean,
challenges?
Me having some challenges. I think I ended up coming probably I think probably had here, but it's just only showing that.
Okay.
Might be doing somewhere that.
Okay, let's try to fix issue with movies.
All right.
And we had a little bit of density matrix in class, right?
What?
We did have a little bit of density matrix theory in the class, right?
Yeah.
But not as much. Probably we need to talk one-to-one more about the background.
All right.
And about I will have dedicated lecture on this SX, SY, SZ on the Wednesday after Thanksgiving. So it will be dedicated for you.
All right.
And then you'll have time at least from Wednesday to Friday to update your written report.
Yep.
Okay, now it's, can I sit closer so that I can type things? Yeah, thank you. So,
So that's just the movie theme song if you want.
oh, it is after the code is runs, it is a second. So anytime we run it again, it's better
Yeah.
to rename, right?
Yep.
Okay. You have SX, SY, Z. How does it work? Let's check. It's here. Plot SX times SX, SY, Z. Okay. So it plots a little dot.
Yep.
And this is not number one. This is variable. L for loop.
All right.
For loop. Okay. And this connects the origin with the point on a circle. Okay. I don't. Oh, and here is a pause. So we save the image into current frame, and then go to the hold off, and then go to the next. Okay. So it's save. Maybe. How do you bring up command window?
Right down.
Okay. Yeah. Thank you. So let's type new figure. So maybe it just behaves in a spoiled way. Sometimes they do not like no run. So now it shows post, press any key.
So this shows all.
And now let's check. Maybe it. Okay. Okay. I have an idea what is going on. It can you copy Control C or whatever? No, it's now let's paste this thing here. Okay, and we're going to run it not for the whole thing, but just escape. From 1 to 2. So it will set up the size of the image as needed. And then let's try to run. Quick. And see if it shows again. Frame must be, it complains about size of the frame. Is it okay to close all windows?
Yep.
Okay. And it is the code that you were changing. Module movie block. Yes. So maybe it's not happy about the size, but it's a little strange. What else? I think it is. Let's just in case if I do something wrongly, call it version S for stupid, because I may do some stupid errors. And then why is let's do hold off and what? Okay. Post in debugger. And how do we?
Sorry to interrupt. I'm gonna head out now if that's all right.
Yeah. Oh, yeah. Absolutely. Absolutely. So you
I think I have
You-
everything I need.
okay? I don't want to pause at all. Oh, quit debugging. Do we see any errors? No. Does it go forward? Line 3, 6, 8. What about, there is no line 3, 6, 8. See it's something. Oh, line 43. Okay. Video object, video writer. And then we need to have the get frame, write video, and then at the end close video object. White,
Yes.
may we request your help as an expert?
I don't know about that.
So I'm just not sharp enough here. So let's show the error message. Let's bring another chair so if you feel more comfortable. Yeah. So this error pops up when user drags and drops size of the panel while it tries movie is being recorded. But I promise neither me or Joshua were doing it. So it tells that size of the frame must be a certain number. So here is the code itself, And you hope you can just check if we implemented these commands correctly. So
Does this W need to be capitalized?
uh, I don't know if it is important. So
I know there have been other times where I've tried to do it and you have to capitalize both write and video. And maybe
Okay.
that-
Okay.
Maybe, I don't
and
know.
where is the open command? Joshua, would you please help?
Command window.
Open. No, in this little script, there should be open.
Open.
Yeah.
Open.
Okay. Okay. Yep. Let's maybe do not write anything there because it's actually not open. So what I was trying to do is to copy paste main cycle, but only for a couple of values so that it creates image of the right size. But now, and it was complaining here. Now we do not write anything to the video. We are opening and then doing get frame. And at the end, we are closing video object.
And there's
Yeah,
that.
capitalize this again.
Okay, save and try to run it in this video. It opens new one. Just press any key. And typically, if at this instant we are going to the command line, it shows. If I did it, it will be an error.
Line 70.
So it complains about size of the box. So let's try to do once again. So PWD LS .m. What's the name of the code? Module. Module block version stupid. So press any key and then we push nothing.
And function or variable right video.
No video frames were written in this file, line 14. Write video unrecognized. Maybe it doesn't like uppercase.
Yeah, maybe.
And what was line 14? I think it is quite innocent.
Yeah. Go back to the command. Right. That's right, video writer.
Mhm. So if we do not solve it right now, just skip it and work on your main parameter,
All right.
accumulating your main observable, and send these versions of the code. So if you,
I don't know.
okay, let's just maybe email this both versions of the code to me and CC to Wyatt, and I promise to meditate during the Thanksgiving and maybe earlier, and email what I find.
It says unrecognized. Unrecognized. Is that right? Unrecognized function right video.
It's something strange and could be something really stupid, like swapping V and W. I can do such
Right.
errors.
So right video is it isn't. It's like it's a command, right?
Yeah, we can
It's like a MATLAB
open
thing.
it. It's
Yeah.
just a script, quite short.
But it thinks it's a variable because it's saying it's an unassigned variable, right?
Mhm.
Because it's not recognizing it. That's
Yep,
weird.
yep. So there could be also a chance of very stupid fix, like completely close MATLAB, open a new, rerun it, and it may work, or open it on the other computer. But maybe let's not waste time on solving this issue and focus on your main scientific thing.
All right.
Send me copies of these codes, and I will try to run it on my equipment and see what happens.
All right.
Okay.
I might send it to you Wednesday because I have a lot of packing to do and gonna be heading out back home on Tuesday.
Huh?
I'll send you the code.
Yeah, you can send right now.
All right.
Okay. How things are going? How many things did you run? Okay. Oh, so something is working, right? Here.
Yeah, this is
do-
1.90
Do you see the increase of the radius?
compared to 1.56. Yeah.
Okay. Yep. Okay, yeah, it's good. I still didn't visit everyone. I went for the second circle. So, Hamidou, what do you like better, the code that Wall is running or something that Wyatt is running? Okay. Wait.
What?
After you're done helping undergraduate Joshua, you are assigned to help graduate student Hamidou. So please exchange emails and send him your version of code. He just need to learn basics of what we do here, because he is deciding which research to do for the rest of his life. Okay, smile to the camera.
I was just trying to look at what parameters I would like to. Wait, so when you say run ab initio,
Run. I don't deny my own words. I can explain what they are,
okay,
and I agree that they're correct.
okay.
But there never was a plan to torture anyone with class attendees. So it should be.
No, but I'm really interested. I know ab initio has more details.
Right.
Yeah, so I really want to know what it entails.
Mhm.
I'm really interested in what it asks.
So please show me some figures that it generates.
So I must have changed something.
It is touch screen. It's so great.
I changed something definitely, and I don't know what I changed. I think X, maybe. I don't know what I changed.
And did remember last time we were plotting emission spectra in the range from 0 to 3 electron volts?
Yeah, I remember.
Did you save this version of the code? So here is a general suggestion. Do not do anything. We're just freely speaking. I'm just sharing my experience, which can be also wrong and stupid. But when I change any letter in the code, I rename the code and save it under the new name, just in case I did something good. We yes, keep original one, and if it was a like natural selection between several versions of code, if by some reason I spoiled something, I can restore. If I did some good finding, I can find it. Okay. Are there more figures? Is there a figure? Okay, I'm probably interested in this one. Yes. Yes. Figure one. Is there a variable named photoluminescence?
They like to find.
Yeah, I know, but I want to refresh in my memory what we are doing, how big is the code. Is it the only code
No.
you have?
This one.
Okay.
No, I don't know the difference.
Maybe the larger the number, the later is the version. Okay, it's better. Now let's.
I think this was the one that you were saying about spectrum. Maybe I.
Can you teach me something? How to bring up command window in on this equipment?
I don't know why it's figured into something else, but yeah.
Okay, and can I jump between them this way? Okay, yeah, I feel much better. So figure states. Oh, I probably need to be less lazy. States eigen. Okay. Busy. Yes, here's your spectrum. Now, do you have an emission spectrum of the complex that you want to model? Which complex you're working at?
I'm working on 13 structures.
What is your favorite one?
One with the NO2s.
So it's better to have something with like gap. Well, show me what you're working at, and we'll select together. Better if it will be PowerPoint with everything summarized.
Oh, okay.
Yeah,
Sure.
true.
Is this clear enough?
Okay, so copper
So
2+
this-
does exist in nature?
No, I'm not working on 2+ because
Okay.
it doesn't exist. No, this is 3. Not
Okay,
2.
here I saw it was 2.
Oh no, it's 3.
Oh, yeah.
Yeah, so different colors, different what's it called? Different groups.
Okay. So I apologize for just asking in the middle. What is the goal?
So
Higher emission and lower transition energy? Or I'm wrong? What is the when everyone around you will start dance and celebrate a success?
so apparently Dr. Kivina says it's too redshifted.
And what would be the perfect redshifted?
700 to 900.
700 to 900.
Yep. So from here to like somewhere here.
Okay.
So most of all this, the first states are showing up two redshifts.
Mhm. So what is this black?
Cyano group.
Is it good in the transition energy?
Using this good because it's also showing up
Too much
too
redshifted?
much redshifted. They're all too much redshifted.
But you've told from 7 to 9. So if you take this pink hydrogen, then it will be better.
The pink is OCH3.
Okay.
I don't want hydrogen because hydrogen is a neutral. It
Okay.
doesn't really do anything.
So OCH3 is better. Is 9, yeah? Okay. So
OCH3 is B, right?
hmm?
OCH3B because
Yes.
B has C2H4 linked on the side.
Oh, okay. I remember. Okay, good. So OCH3, good. No. Well, we can do even other, but NO2 looks like biggest
Yeah.
shift.
it's
Now,
much.
where are experimental data?
Yeah, so that's I don't have experimental data for copper. What Aaron initially worked on was with is it indium? Now I'm always mixing it up. Is it indium or iridium? I'm always mixing it up. Indium, I think.
Indium.
Yes, indium.
But I know that you're doing 1,000 things in parallel, but maybe you were reading some papers. Maybe
Yeah.
Dr. Soon and you and your boss are not the first people in the world who do emission of complexes.
So yes, people have done copper complexes, but most of them do not show up in the range 700 to 900.
But other generally bright copper complexes that emit at least something.
Yeah, but it's in a very low range, like it's in the 500, 600.
So two
No, sorry, that's absorption.
absorption and other complexes that emit, copper complexes that emit.
No, I don't remember.
To your maybe there are, but you haven't seen such papers, right?
Maybe there are, but then I haven't taken note of what most of them are showing up in the emission. I've only taken note of what they look like in the spectrum.
But emission is a key parameter, so it would be cool
Yes,
if
it is. I
you.
don't know why it's just not.
Mhm. But NO2, even if it is wrong and not the final goal, it's so pronounced. It's emission and it is redshifted. So maybe we can look on it. So if
Yeah, I mean, I like the NO2. I always choose it, but like it's too redshifted. So
but it's like cooler effect, maybe because of charge transfer.
yeah, it's a stronger electron withdrawing group.
Okay. Now, do you have what is the image of this NO2? Maybe the most redshifted is NO2A. What they are?
What it looks like, right?
Yeah.
Okay. Does this do anything? Do you see anything like this? This is NO2A.
Okay, good. This one, right?
Yeah.
Okay.
This is
Is it ground state or excited state optimization?
this one.
Uh-huh.
This is excited state. S1.
Optimized for excited state. And you do also have the geometry optimized for ground state.
Yes, I have both.
So if you overlay geometries of ground optimized and excited optimized, will you see any differences? What changes upon optimization? Which group of atoms moves?
I haven't tried.
So please try, not for me, but just for yourself to learn.
Sorry, hold on. That's between S1 and S0. Is that what you're saying?
Yes, exactly. So what is moving? Is there a change in geometry?
So how I might have done this, but I don't know. How do you do the overlay? Like what sort of things do you do in the settings?
In PowerPoint, I'm speaking very stupid and basic things. just as an example, it's not a final answer. In PowerPoint, you can make your image transparent, right? If you do image of ground state geometry transparent, excited state geometry transparent, and put them one above another, you will see through as they're printed on the glass, and then see are they literally replicas of each other or something is moved. It's not orbitals, it's just geometry, positions of atoms. So which atoms move when you optimize excited state. But if you do not have this preliminary data, maybe we can postpone it. If you want to add it to this project, then you prepare this data, we discuss them, and during the break, and then try once again. But right now, let's put a goal for this little study to reproduce, let's say, this spectrum. Okay, so the transition energy will be about 1 electron volt, right? Approximately 1,200 nanometers, about 1,000 electron volts. Right now we set it up as 1.9. We need to put it around 1. MATLAB. Yes, here. That's it. So simple. Now let's look where is DE off. DE off. So we need to do a bit of homework on transferring. So we need to express energy offset of 1 electron volt in atomic units. So
you're going to convert that to atomic units.
yes, yes. So if you have one electron volt, we just divide it by 27, so it will be like about 0.37. Okay, now there are.
Does this parameter have anything to do with?
Yes, yes, but it is too early to speak about it before you compare excited and ground geometries. As a starting point, it's not so bad, but after we discuss, we may modify this parameter as well. So X equilibrium, those are 2 key parameters. And so the goal is to manipulate parameters, specifically these 2 parameters, maybe only keep one of them fixed, another changed, until this spectrum, sorry for touching, I always forget that it's touch screen, until this spectrum replicates this one, or starts looking approximately similar to this one. And let's agree that we will not do more than like 10 runs. If in 10 runs it doesn't coincide, we will just select the one that looks better. Just because your time is precious and we cannot overuse it. Make sense? Now let's just learn what are these parameters and how they affect the spectrum. So they do enter into potential energy surfaces. So here is potential for in one state, here is for another one. If you look, see they're blue and red have minima slightly offset, right? And we can agree that we keep maybe the blue, which is 4.9 fixed, and the red, which is no, we should keep red, which is 5 fixed, and blue, which is 5. Sorry. Changed. Just change them. Maybe try to use it like 4.91, then 4.97, 5.01, several values. So this will offset these things. And as you do it and repeat this first this code and then this code, then it will redraw the spectrum. And after doing this manipulation, you will see how manipulation of this parameter affect the spectrum. So let's do this practical thing and try to record these images anytime you run the code, and then we'll sit together and analyze. I would be very happy to go over the code and discuss more details. I just need to talk to other students. Is it enough as a starting point?
Sure. So the two parameters I'm waiting for now is just
Only one, XEQ1. Change value of this parameter.
Why am I doing it?
Because it is excited. No, EQ2. Sorry. The excited state. You keep grounds same, and you haven't compared ground and excited state. You do not know how much they're different. So we try to guess. If you have them equal, it means excited state geometry is equal to ground state geometry. If they are offset, it means something is changing upon excitation. Okay? Yeah, thank you. You need to go? Okay, it's fine. Okay, now it's time for online company. Sorry guys for delay, but at least 20 minutes are yours. So I need to make you guys how you call it, co-host 1, co-host 2. So Joe, would you like to be the first?
Yeah, sure.
Please share screen. Wow, this is really cool. Yeah. But Joe, you are doing a project of MyCSI.
Oh,
It is basically what she's expected to do. So you may want to cooperate and exchange emails, and you guys can learn from each other. Mike, do you see similarity to what you do and what he's doing? So Joe, right now you are selecting a simple path, a shortcut to use only orbital on a circle. By the way, does your microphone work?
yeah, it does.
Can
you not hear me?
Something?
Try something different here.
I don't hear. Okay, you can type as needed. So
I can hear.
if you want to go
You hear me
this
now?
way,
Hello?
you need to convert. Oh, you can hear him, but I cannot. I can try enable sound on other computer.
You guys hear me now?
Yes. But it creates feed, back.
You guys still hear me?
Do you hear me without feedback? Do you hear
Yes,
me?
yes, I
Okay.
do.
Whew, much better. Okay, so do you have email of my CSI?
No, I do not.
Do you see her email in the distribution for the whole class?
Yes.
Okay, do you have the email of Joseph Dieter? You should see his email in the distribution for the whole class. Just look based on the name. Joseph Dieter. So please just talk to each other, maybe share codes and explain what you're doing. My plan was that you will be doing different things, but just in case you are colleagues, you are like on the same side of the barricade and you can cooperate. So now I'm talking primarily to Joe. Joe, Mai was asked to run similar things as you are doing right now and save each run as a movie. So
Okay.
Current version of the code doesn't have commands for movie, which will be like open video writer, get frame, close video writer. So they need to be added in a correct thing. So if you want to go this way, please add them. And
Okay.
then we cannot have two people doing absolutely the same, but you can do it as a little training. So I keep talking the story, what Mai is doing. She is trying, can you please bring up the code, not the images, but the actual code? Yes. So in the line number 6, there is a variable nodes. You see it, right?
Yep.
Okay, so the task of Mai is to change value of variable nodes, maybe by like 0.05, change the name of the output video, rerun the code, save, upload video to YouTube, and then repeat this procedure for many different values of the nodes variable, and then report observations.
Oh, okay.
So we will design slightly different, or maybe not slightly different task for you, but just so that the meaning of this process is that variable nodes controls magnetic quantum number.
Right.
So if you take the value nodes equal, let's say 2 right now.
Okay.
Save and run and see on the image what happens. I think figure 9. So you see it almost nothing is happening, right?
Right.
It looks like movie without actual motion.
Yeah.
So because you see these green lines, there is a black circle and then green line that goes out, in and out of the circle, correct?
Yep.
So if after 2 periods, it finishes at the same place where it stopped, it means it makes full cycles. So nodes equal 2 would correspond to a d orbital. Two positive and 2 negative. And if the number will be different from literally nodes equal to, if it will be less or small, then the image will look much more wild and ugly. As you saw for nodes equal 0.56 that you ran before.
Right.
So basically it is a proof that in Bohr model, the angular momentum should be quantized to an integer number. Make sense?
Yeah. I think one question I do have, so if this wasn't what I was supposed to be doing, but I guess for the
you can stop this code right now and let's discuss the second code.
Sure.
Okay. Now, please keep asking, and yeah, I'm very happy you're clicking on this code.
So when you said for like I needed to change values of m,
Yes.
was that a variable on this code?
Yes.
Because I was scrolling through it and I couldn't find it.
Okay. We will try to find. I'm requesting control over your screen.
Okay.
Thank you for granting. So there should be a place where initial condition is set up. When we did anyone thinks it's time to leave? Anyone needs to leave? Yeah. Okay, Joe, just a second. You got basic idea what to do, right? Yeah. And please communicate with Joe because you should be thinking in a similar way. Okay. Yep. And send me also emails as needed during the break. Thank you. Okay. Yeah. Thank you. So I continue talking to Joe. So when we were doing the same problem for everyone in class, when, for example, when we were considering the free space, most important part of our task was to select initial condition, initial wave packet, right?
Yep.
Okay. So and it was stored in the variable psi naught, correct?
Yes.
So and you remember that psi naught was a product of a plane wave, right?
Yeah.
And Gaussian function, correct?
Yep.
Then, if we would like to do the same thing, and now it deals very much to what Sibel is doing, right? So if we want to do two-dimensional wave packet instead of one-dimensional, then we need same plane wave times Gaussian along another variable. So first for x variable, you see?
Yep.
And then over y variable. And at some point after this, we should multiply these two functions and make them as a new initial condition. So I will find where it is set up. But it is not the whole story.
Right.
So it should be something like this: product of psi naught of x and then psi naught of y. So it will be actual initial wave function. But this is not the whole story. The actual story will be later. Yeah, when I was sending you this code, I think I was trying to focus your attention on this line. Do you remember or not quite?
Not quite, no.
Okay. Do you have the link to, or do you have, let's do together. Please bring up a browser.
Okay.
With maybe Google to search.
Okay.
And type hydrogen atom functions. Okay. And just go to any of the links. We will inspect a couple. If it goes too long, okay, let's scroll. Let's scroll, and see. Yes. Okay. Enough. They stop on the p orbitals. They do not show d orbitals. But if you look for other sources, you'll see the list of this of the similar solutions for all orbitals. So what are the three numbers as an index of phi?
It's the state, the eigenstate n, I think, angular momentum and
Magnetic.
magnet. Yeah.
So three quantum numbers: principal, orbital, and magnetic. Right?
Yes.
So the principal quantum number defines dependence on r, on position from center. And here it shows only this, or my index, r times e, it should be e minus r. So it goes up and down. And
Okay.
then the orbital and magnetic define dependence on theta and phi. Theta is not important right now because your program is two-dimensional, dependence on phi. So here m equals 1. So it means we have I times 1 times phi.
Okay.
And this is p orbital. If it would be d orbital, it will be I times 2 times phi. Make sense?
Yes.
Okay, now let's go back to your, please bring up the MATLAB code. So the variable that is not variable, it's to some sense my fault. Let's call it nodes. You see it?
Yes.
And make little marks that it is in line 185.
Okay. Sorry.
Yeah, and I'll do it here also. No, here is not needed. Yeah, good. Now I'm going back to the very beginning of the huh? Yeah, take a seat. I don't know how. I hope it will be quick, but who knows? So I'm going just to go to the very top of the script and set up the variable nodes because it will be main thing for you to change. So nodes equal to, and if we may change it like 2.1, which will be wrong but interesting.
Right.
So main thing to change. Basically, you change this variable, rerun the code, and report the result.
Okay.
Would you please navigate back to this line 195 or whatever?
185?
Yeah, I think it's much easier for you. Okay, thank you. So let's read. This is a main line in the whole code, at least from the point of view of your project. So alternative product psi. This variable psi will be initial condition.
Okay.
So the Hamiltonian is set up to mimic hydrogen atom for two-dimensional dimensions. And here we are testing. Instead of solving eigenvalue problem, we are guessing the wave function and then practicing evolution operator, practicing time evolution of this wave function. If it is an eigenstate of the Hamiltonian, it will not change or will change minimalistically. We will show just some beautiful little oscillations. If it is not an eigenstate, it will explode, decompose, make some ugly motions.
Right.
So by trying this code with different value of the variable nodes, you will be able to manually solve Schrodinger equation. So there is a smart mathematical naming for this method of solution. I'm just not sharp right now. Now let's focus on this equation. What does it model? So we have dependence on rho, which is distance from the center of atom.
Yep.
So rho is distance. Ij are indices corresponding to x and y. So since it is a circular motion for different x and y, rho will be different, right?
Yes.
Because I and j map any point on this plane. So we have rho squared, right?
Right.
To the power 2, and then exponential of minus rho.
Yep.
This is second order polynomial, which comes from the solution of the Schrödinger equation for d orbitals. Now the dependence, we do not have dependence on theta angle because we do not have theta angle, but we have dependence on phi. So it is rotation. So angle phi is also defined differently for different points x and y, right?
Right.
So to be able to set up this initial condition, we need to define how distance and angle depend on x and y. This is not your task. This is like an input part of the program. But if you're curious, I can briefly cover it. So we scan variables x and y. So for each I and j, there is a x of I and x of j, and then we do x squared plus yj square root, right? So it will be radius from center,
Yes.
and then for then y divided by x will be a tangential trigonometric function, correct?
Yes.
And then inverse arctan will be angle.
Okay.
Right? So if you define radius and angle, we can use them as parameters to set up our initial wave function. Make sense?
Yep.
Okay, so this is a main thing. From now on, you can run the code yourself. What is maybe we just to so that you feel more comfortable, we should identify where the Hamiltonian is set up to so that you feel more independent. Okay. I think we briefly discussed it with Sibel. This is the most challenging and important line of the code to make it work. So we do have Hamiltonian in respect to variable x and Hamiltonian in respect to variable y. But instead of multiplying Hamiltonian for x and Hamiltonian for y, we need to do composed Hamiltonian. So operator acting on the x variable multiplied by unity operator doing no change to y variable.
Right.
Plus unity variable affecting x variable times Hamiltonian affecting y variable. And the most challenging trick is that I think if I ask Sibel, she will tell it, but probably I will repeat. But listen, I believe you're able to repeat my next 2 minutes of speaking. So, and why it could be interesting just for curiosity. When we have one-dimensional problem, our wave function is one-dimensional array, and our operator is two-dimensional matrix. Right? If we go to 2 dimensions, then our x dependence is one-dimensional array, and y dimension is one-dimensional array. So together it will be two-dimensional matrix, right? And operator will be 2 times 2 4-dimensional tensor, which is a little crazy for humans and crazy for MATLAB. It is designed to deal with square matrices only. So we need to do operation, how to convert 2-dimensional wave function into just one column and 4-dimensional tensor into 2-dimensional matrix of a bigger size. right? Therefore, we practice this index, which combine this I and J values to something that runs over bigger set of values, but make the job. Whew. Sybil, would you be able to
Yes,
teach
I can.
someone else next time?
Yes.
This thing? Okay. Joe, does it make sense?
For the most part, yeah.
Okay. Yeah. Maybe exchange emails with Sybil if you find it challenging. It will be
Okay.
good training for her to try explaining. Okay. And this was only kinetic energy. There should be also a piece where we add potential. So here, potential V of I1, I2. So when potential contributes only to diagonal part of this four-dimensional tensor. And now the Hamiltonian is big Hamiltonian 3. So it's method 3, but it big because we are in 2 dimensions. And the rest is very similar to what we did before. So we said big G tau 3. Angular field is magnetic moment is 0, so we shouldn't look on it right now. But later on, if you want to explore magnetic field, all components are there. Right now, it's enough thing to play with without it. But this is evolutionary operator, right? And later on, we should see the loop that goes over time. So here, loop. And as we go through the loop, there will be, we need big psi. Yeah. So this is like main time propagation. Big psi of the future equals big psi of the past times evolution operator. So everything is done, but now one needs to decompose wave function from one-dimensional column to two-dimensional color map. So psi 3xy. So we convert from big X index to this individual index. And after that, nothing else. One can, later on, there will be command to plot this psi 3xy and save it into the movie.
Okay.
So surf xy probe 3. Okay, I think it's enough for introduction. Now let's save and run and see if there will be any errors.
Okay.
And please make ready your patience, because this code is, as you have probably noticed, takes much more time.
It's quite long. Should I just go ahead and get rid of all these?
After code has started, it's not a good idea to close Windows.
Okay.
Or you can stop code, close Windows, and then restart.
Okay, I think I'll do that.
Adam, thank you for your patience. We are very close.
Yeah, no problem.
Oh, thank you. Thank you. I really appreciate it. So while it is preparing,
My question.
yes.
So basically, since I'm doing, I'm looking at the. So basically,
Eigenstates?
yeah, I guess yeah, but I'm looking at the eigenstates and whatever. Not that since the reaction is not done, So I'll have to look at it longer at the first 5 minutes and see basically like how I've been looking, which will take a lot of time. So that I could get a more beautiful probability over time.
Even short time dynamics is enough to extract the rate of transition.
Okay, so even like this, I can still.
Yes, yes.
Okay. So I don't need to.
No, you don't need all time.
Okay. That's all I wanted to ask.
Okay,
Okay.
good.
So that's all.
Oh, thank you, thank you.
Yeah.
And I'm really excited and interested about your
Yeah.
project. We should talk more.
Yeah. So you want me? So I should show the eigenstates, or like should I just
Well,
should I show the eigenstates over?
it's not
time,
mandated, but
or
it
should I
is.
just show one.
Eigenstates would be much more important for Joe.
Okay.
But let me speak to both of you.
Okay.
Joe, are you on connection?
I'm still here.
Okay. If it takes too long, I will talk to Adam and then return to you. But the basic task, which will keep you busy and will be sufficient minimum, is just to change the value of nodes, run the code, create movie for each of the run, and report observations.
Okay.
There are additional things which could be really beautiful, and they are not as scientific results, but they increase your understanding, and they will attract attention and make audience scream of happiness. So if you will, at least part of the audience, if you find the eigenstates of this Hamiltonian and plot them, and Sibyl already has the code to do it. She can share it, or I can share it, or we can discuss how it works. It takes Hamiltonian independently from your propagation of dynamics, and you'll find all eigenstates starting from the lowest one and plot them.
Okay.
On one hand, you are manually finding eigenstates by tweaking the nodes parameter, right?
Right.
On the other hand, there is a procedure that solves for eigenvalue problem. And then you yourself will redo all atomic wave functions like S, P, D. They will just pop up their energies and their spatial form. And just by comparing results of direct diagonalization, I think now you can push space. Just push space. Rerun the code, do change nothing, and run once again. Do not just yep, you can close and run again. It's the simplest. It's there is a bug that I always forget to fix. There is an apostrophe changing a row to column, but if you run twice, it compensates each other.
Okay.
So if you find eigenstates by two independent methods, once by tweaking nodes parameter manually, and second by direct solving of the Hamiltonian, you will have independent confirmation that your methodology is correct. So for us simple guys, it's not as important. Solution is a solution, but if there will be a person with critical style of thinking, it will be a very strong argument. Lola knows people with critical style of thinking who are asking questions during seminars, right? So, Joe, you have heard the laughter as a confirmation of my words.
Right.
Okay, so your basic goal is to rerun the code like 10 times with different nodes parameter and make movie out of it. And your super goal is to find eigenstates and make a comparison.
Okay.
Push space. Okay, and now do nothing and just watch what happens.
Okay.
So do you see if you move your mouse, but do not click on anything, it can spoil outcome. Slowly move your mouse to the right panel. Yes, here, and do not click, just here. You see that there are a little white stripe across this blue cloud.
Yes.
So it is discontinuity in our shape of d orbital. So we have corrupted d orbital. Instead of continuous structure, it has a little nodal plane inside. And because of this nodal plane, it will show some vivid, some dynamics which will show that state is not conserved over time. If you would have the nodes variable literally equal to, the shape of this right panel will stay the same and slightly rotate over time. With this little change, the dynamics will be more vivid. And when later you will rerun this code yourself again and again with bigger or smaller values of nodes parameter, this level of corruption of the d orbital will be bigger and bigger, and you'll see some more vivid dynamics which will signify that your state is not an eigenstate anymore. Make sense?
Yep.
Okay. From my point of view, you're ready to go. Do you have any quick questions?
No. Other than just I guess as far as data collection go, I just need to make like a movie of all my different runs for this.
Right. And you should plan your time accordingly. It's not very challenging, but it's time consuming. So the code on Sibel computer, this code takes like 3 hours to run. And if you plan to run it 10 times, maybe you need like 3-4 days. So you just set it run, leave on a table, and then do your other things.
Okay.
Okay. And I invite everyone to send emails to each other. You can, some of you can just get help from each other, and others can get self-esteem higher by helping others. But sometimes you can help each other much better than I can do, because you find better words and you have first-hand experience. So do not hesitate to send emails directly to each other. Okay, Joe, if you do not have more questions, you are welcome to disconnect. Not disconnect, you can stay connected.
Yeah, so that's the problem.
So it will be turn of Adam and Sibel. Do you have a quick?
Yeah, quick question.
Yes, please do.
Okay, so when I go for to find my rate or whatever.
And Adam, just a second. Adam, you can start sharing your screen.
So
Okay.
My initial momentum various time.
Uh-huh.
And hold on, let me put the oops. So my probability graph over time still looks the same even after I change my p-naught.
Okay.
That's why I was like,
Okay. There could be.
I need to monitor the reaction for longer.
Wait. There could be. I wouldn't say big problem, but a problem that we need to address before you get to production of the data. There is a chance that these images are provided for one-dimensional component. They are just a little, how to say, heritage of the one-dimensional version of the code. And we need to do the same thing for two-dimensional, which is not a big deal. It's just couple lines, but maybe I need to, you can start thinking about it,
Okay.
how to convert your two-dimensional probability distribution into probability of left and right.
Okay.
Basically, everything that were nitrogen to iron coordinate is bigger than half cell will be product. You should be able to do it yourself, but I'm really willing to contribute, and maybe when I'm a little sharper and fresher than now.
Okay.
But thank you for identifying this.
Yes,
this
yeah,
problem.
because I wanted to. That's what the issue
Okay.
is. I cannot
Yeah.
split my mind.
Yeah,
Thank you.
that's great. That's great. Yeah, thank you. Okay, Adam, I'm listening. What would you like to tell or ask, or please lead the discussion.
Okay. So we discussed porphyrin donor bridge acceptor systems, right?
Yes.
I found a paper kind of describes fluorescence experiments that they did, but it lists some values for delta G naught and some rate constants. But I was wondering how difficult it might be to implement maybe some of these values with specific solvents into my code.
No, it's completely not a problem. It's very doable.
Oh, good.
So, let me suggest that we please send me this paper first.
Yes. Yes. Yeah, I will send it in the chat. Okay.
Email is better because
Em-
I can close our connection and then the chat will be lost.
Ah, okay. Sounds good to me.
Sorry for inconvenience and sorry for myself being picky.
Oh, no problem. I have to do the
Yeah.
authentication. Okay, should be good. Yes. Okay.
Okay, enough. Just send. Okay, you're so polite. Okay, so let's go. So first thing I would look through and we will. No, keep sharing screen.
Oh, did it stop? Oh,
I wish we
sorry.
can finish everything so quickly. So let's go back to MATLAB. I'll
Okay.
look through the paper and I do not see any big difficulties to implement the values from there, but let's try original plan and scan the energy offset.
I did. I have 21 different runs with increments of
How many?
21
Okay.
already. I mean, I noted the rate, and I took at least photos of this window and this
Good.
window
Okay.
for
Okay.
each.
Yes.
But yeah, I've all of the runs kind of documented. Yeah.
That's great.
Just-
That's absolutely great. So, did you record? Thank you, sir. Did you collected the del E off and alpha rate from
Yeah.
each run into the like Excel or like a table to plot?
I've yet to tabulate it, but I have all the values in these slides just to have them compiled
Okay.
somewhere.
But
But it would be, yeah, that'd be my next step.
But it is much quicker and easier to complete this analysis, and it's much easier and quicker than to modify parameters to match the paper with different solvents. So
Okay.
you should complete it. And please, although it is not yet plotted, please guide me through. You can also send me this intermediate results as an email later, but please guide me through your data right now. I'm very curious, so just spending maybe 20 seconds per each run. Start from the first.
Okay, so this one we started at negative 0.015.
Okay.
This for the offset or
Okay.
the
Yeah.
negative delta G.
Going-
The rate was very low.
Keep going.
The next one it's increased by 0.0015. And the rate is expected to go up, and it does. It does go up again for run 3, 4, 5, 6. Now it starts increasing by significantly more. So I think by the time we reach run 10, I start to notice something, or in run 9, I start to notice something different with the position time graph. And the rate starts increasing significantly. And so Here is when the rate starts going up, I think by at least factors of 10.
Okay.
But run 11 actually goes up to 1.33 times 10 to the negative fourth.
Okay.
It goes back down.
Yes, it's so perfect.
as-
It's so perfect. Yes, I'm happy. Okay.
this increases again, but it comes back up with this.
Okay.
Not quite as high as the other one, but just about similar. And then it just begins, it goes down again, it goes back up, goes up slightly more, and then falls down. But then it just, it shoots back up to power of -4. Or
Okay.
10 to the power of -4.
Uh-huh.
So yeah, it goes down, up, and it concludes on this this rate value here. So
Okay.
the rate seems to just fluctuate. It doesn't exactly, I guess, follow this, but it's sort of exactly what you said. It goes up and down.
Okay. So it would be simplest and very interesting to immediately plot. And
Yes.
you know, if you summarize this data into text file, one can plot it in MATLAB instead of Excel. Just
Oh,
put
okay, good.
text file into MATLAB and then generate all figures in a consistent way. And then we can try to analyze what's the reason for rate going up or going down. Why it goes
Yes.
up and down at certain values.
Yeah.
And this will be a little discovery, which you will get for cheap. And then after the only possible technical thing, maybe if the fluctuation is really big, you can do a couple of additional lines for the values of energy in between.
Yeah. Yeah. Fill in the gaps a little bit. Okay.
Yep. Yep. And do not overload you with yourself with tasks. Just analyzing is more valuable than accumulating more data. If you let's do analysis, and then if you feel hungry for more data, you may implement the method for computing. Check that your code does this integral method of rates, as Wyatt was asking about. Let's discuss. Let's do the figure first and some analysis and hypothesis what is going on.
Okay.
And I would be really curious to compare your data versus this parabola that you were showing a second ago. What? You are typing? You're so not lazy. I would do copy paste.
You would copy, okay.
I would just copy paste your text box and just erase text in between two numbers.
Okay.
Let me request your remote control. And
yeah, sure.
Okay, thank you. Can you type Control C to copy and come back to your text and then paste and then
just continue to do this.
Just yes, but we can do this and this.
Ah, okay.
Okay, and then continue the pattern to collect numbers. Whatever.
So I have two questions. So for this,
Adam, I will quickly chat to Wyatt, but raise your voice if you immediately need me.
Okay.
For this table, and for like analyzing different ones, do I just need to have one where they're all the same, like no difference, and then one other one where it's shrunk, or should I do more?
With a kink?
Yeah, or should I do multiple kinks with different lengths, or just one?
your time is valuable resource, and I would do one kink, maybe substantial kink, where
Like
there is a gap.
0.5 or
Yeah, and do just another set, and then go into analysis. And if you see that there is no big difference, then maybe do another one. But
Okay.
Even if you are really enthusiastic to do something, just consider your personal time as a,
Right.
as a valuable resource.
And then, does this look right?
Yes,
Okay.
but you are plotting it as function of time, right?
Right.
Try to plot it as function as 1 over time. Can you do it? Use this as
Well,
x. Use this as x and this as y.
It is. This.
Huh?
Yep. This one is y. And this one's.
This is x. Are you sure? What is plotted here? What was?
So these are negative numbers, and these are on y.
Okay, and
I should probably increase the zoom a little bit.
so
This is for something with no kinks or anything.
okay. Okay. The smaller value corresponds to more realistic temperatures, right? Higher value correspond to something like on the surface of a star. Yeah.
Yeah.
So let's maybe focus on the.
So have more, start more values in there.
Yes, and just erase. Can you navigate to narrower edge? Yeah, and maybe less. Less. Huh, interesting. Even less. Even less.
And what if we do that?
Interesting. Maybe exclude the very first and do like first, second, and third. Okay. Oh, okay, okay. Nothing is wrong. I just see
Okay.
why it looks the strange way. So, if you would look for the movies that are happening at high temperature, you probably would see that the wave packet just runs through as a
On the high momentum.
high space as a free, as in a free space. So it doesn't care whether there is polymer or there is no, right?
Yeah.
In this range, it's same as a free space.
Okay.
So we need only much smaller values, and also here you increase it linearly. We need to, well, you do whatever you find reasonable. Just another suggestion. Change momentum in such way so the energy increases linearly. Right now, if you increase momentum linearly, energy increases quadratically.
Okay.
But if you do like increment of momentum gets smaller and smaller, as approximately as square root 10, kinetic energy will get linearly.
Okay.
And start from smaller values.
Okay.
So maybe this 0.2 is maximal. 0.2 is maximum. In regular chemistry, we rarely go above 1000 Kelvin unless we do the like molten iron with a target reaction.
Okay. So then.
Silicon melts at 700 Kelvin.
Okay.
So yeah.
So then, looking at like the smaller momentums, then it's going to be a very, very tiny yield of rate of reaction, right?
Can you focus on only the first and second? So if you would have no time to complete this at all, if the presentation will be due tomorrow morning, you would make the straight line through these 2 points and extract the activation energy from the soul.
Okay.
And
But it's negative. Right?
that's fine.
That's fine. What negative?
Because Boltzmann distribution e to the minus activation energy divided by
Oh,
KT.
right. Okay.
So it's completely normal, right? So these 2 points are available, and this is just a tax to your enthusiasm.
Okay. So very smaller smaller values, and focus on having kinetic energy going linear instead of momentum. Okay. And then do that for both.
Right.
Okay.
Yeah. Thank you much.
Thank you.
Much. Adam, you are a very quick worker.
Is this the correct syntax for this sort of?
I would do it a little different way. Do I still have your permission?
Yeah.
Okay, thank you. PWD. Users Adam desktop PC cam project. Now do this one. File save as to this. Yeah, please save to this directory and call it. Okay. Now let's go back here. Do you have that your data? Yes, data. Yes. Now we can call data equals load data dot txt. What? Oh, let's. Yeah, it's enough. We can either redefine variables because data is your exactly your thing, or we can just do plot data everything for the first column, comma data everything for the second column. Can you please bring the panel with figures?
Yeah.
Okay. And that's fine. That's fine. Do not worry. And if we do log would you please bring up? Okay.
Yeah.
And now do you still have the image with your Gaussian thing, or we need to replot it?
Oh, I can.
You can copy paste the part of the code. No, it's better to plot the things on the same. Just show me the line that does it.
All right. It's
okay.
this.
Okay. List, and now let's show what is on. Okay, yeah, I see it. Now let me combine these 2 things. Yeah, that's good. I'll do it.
Okay.
So comma and just would you please copy this thing?
Yep.
And paste the and paste here and enter.
This is the white label.
Oh, yeah, my bad.
Yeah.
So let's bring the line. Yeah. No, only plot.
Oh. Okay.
Either enter or Control C. Just click enter, and now arrow up to bring up. Yes, this one. And now I'm doing arrow up, comma. Well, I think you control is yours, comma, and here I just type data colon comma 1 for x data, and we need log data colon comma 2, and we can use symbols like O. Okay. Maybe log is not a good idea. Let's do it without log to see a more favorable comparison. Okay, better. They are off by less than order of magnitude. They are off just by 5 times, right?
Yeah.
That's okay. That's okay. So maybe we should take a couple of additional points in between. But I guess the total number of these peaks will be no more than 8, even if we do very fine calculation. So it could be individual resonances between vibronic frequencies.
Ah. Okay, well, that makes sense.
Okay, but adding more points would be really cool and valuable.
So you're thinking between around 0 and 0.1?
Yes, just a second. Why it is departing, I want to answer him. Right. Okay. And after that, this lab, you will do the text report. And before presentations, we will have another lab just to make sure your videos are working, just last final touch. Okay. Thank you. Thank you. Yes, Adam, I'm back with you.
Okay, so more points between 0 and 0.01.
Yes.
Okay, okay. Yeah, how many do you think I should grab 20 points in this range or?
Well, it's a creative task. You set task for yourself, whatever you find.
Okay.
Just to understand what is going on.
Yes, yes.
Okay.
Yes,
I'm listening. I'm listening.
Is there any way that I could output the data from this into a text file that I could call to kind of plot this like that?
Yes.
Yes.
So you can collect this command. So copy this command and the one where the data were read. Just so scroll. Yes. So this command and the plotting command, and paste them into wherever you have right here.
Okay. Perfect.
And then it will go automatically.
So it'll output the data from individual runs here into the text file.
You can load. You see data equals load data txt. So if the data txt will be already saved in this directory, it will load and then you will plot it, right?
Okay, that makes sense.
Okay. Do you remember figures where there are potentials and the eigenstates together?
I do. Is it?
Right now, let's postpone it for the future. But I think this figure with potentials and eigenstates will be a key to explain differences between Marcus formula and your results.
Okay, interesting.
So let's talk more. I think we are a little over time, and maybe Hamidul has questions. So But I think we completed the full circle. If you want, you can stay here, and I want to talk to Hamidou, and then later, if you have more questions, I'll answer. But if you feel tired, feel free to disconnect. Okay, yeah. I will. Oh, we don't have class on Wednesday. That's right. Yeah, therefore we are doing this makeup lab because so that no one we do not have a fear of failure. It's critical to have today's class, and then we are safe to do the rest. Yeah. Okay. I will send you emails then over. Yes, and feel free to request in one-to-one meetings. I'm not very busy during this break, and we can set up quick Zoom meetings one-to-one if needed. Perfect. That works great for me. Okay. Okay. All right. Thank you. Yeah. Thank you.
Well,
Okay.
it doesn't look good to me.
Do you have any new spectrum?
So let me just show you everything.
PowerPoint?
No, so I saved it.
Oh, okay.
So this is all of the value spectrum.
Yeah, it's better to save all the graphical images than put it in PowerPoint. This because when you load this MATLAB style images, it will change settings if you are computing something else. So it's better to save just. But let me tell you something. The values.
Yeah.
Try to be. What's the word? Gentle, another word, conservative. So do very little change, maybe from 4.9 to 5.1. This is too wild. 3.9, 4, 4.5. This will. It's too much of the. Just make little changes. Oh, okay. What are you doing? Do not do it. Don't. No. Wait.
Supposed to click it once, right?
Click it once. If you click it 3 times, it means like it is a you submit three jobs into queue.
Right.
Now you need to click press, and then if you run the code, and then.
So which one is, how do I know which one is 45?
Right.
The old.
Right now, if both are 5, then they do not differ. They exactly one above each other. You understand?
Yeah.
Okay.
They are both 5.
Yes, and then slightly start to change excited state either to left or to the right, and see. And after you run this code, then run the second code which generates the photoluminescence spectrum.
Oh yeah. Okay. Can I go?
Oh yes, absolutely. I think it's too much. Camille, how are you?
Yeah. Also, yeah, I wanted to ask something.
Yes.
Is there a way I can manipulate this? Because it seems like there's too much space here, so I can't really see.
Oh yes, absolutely, absolutely.
What value? What parameter is this?
Teach me how to bring the window.
Okay, it's just here.
I want to see simultaneously. Window. So I click to select this figure, then now I'm facing consequences of someone clicks
Too much clicking.
too much clicking. Yes,
Sorry.
yes, yes. I think someone got nervous.
Yeah, because I'm like, I'm
Um,
tired. Why are you not doing anything?
An artistic painter became a surgeon. and, then, and then he makes surgery. Not,
I'm tired.
Yeah, sometimes you get frustrated.
Yeah.
it was more than 3, it was like 10 times. It's okay, it's okay. Control C. Control C. Control C. Control C.
I bet you I clicked this thing like more than 10 times because I'm like,
No, it writes here press space when you're ready to see the movie.
Can you just all close it and then open it again?
Yes, we can, but Lola wants a question how to manipulate.
Can you just tell me what parameter this is?
What?
Can you just tell me what parameter it is in the command window so I can just do that?
Yes, it's possible. It was like 20 times.
I can bet you were like 20 times.
Oh, whew, finally.
How can you tell that it's done?
Because it doesn't ask anything. It shows prompt and it responds like
Oh,
who am I? It doesn't know, but at least it shows ls. Good. So, but it who variables. Okay. So we want manipulate the axis. Axis, round bracket, rectangular bracket, and then we probably still want from 4.7 to 5.
yeah, it's the y-axis.
Yeah, but we still need the whole box.
Oh, yeah,
2,
sure.
and then y goes from -0.1 to
Like
0.2.
0.4 or 0.3.
Okay.
Yeah, this is fine. So I can see it better.
Okay, and you can copy paste it inside the code. Make sense?
Yeah.
Thank you for your patience. So can we do which one you like better? The one from white or the one from?
I have both, and I think he was doing some really cool stuff.
Okay.
here.
So you have you press when ready. Same as cool. And then when it is done, it will create a movie which you are expected to upload to YouTube and send me a link. So that I see this movie how it works, right? Movie, yes. Wait. Do not take example from all. Wait until it is done. That's okay. That's okay. I'm kidding. So see, now it is done. Okay. And if this same as it is. MATLAB. Okay, it was MATLAB, but it doesn't have it. Now open your Google Gmail account. In some browser, or if you have mail or you immediately YouTube. If you have Gmail account, then
No, immediate from
YouTube. Okay. Now click plus. No. Plus. Plus upload video. Good. So it has. Go to your MATLAB.
So I spell it wrong, right?
Yeah. I think yes. Well, unreadable. Yeah, something is wrong. Let's go back to MATLAB and see what is going on. This one? Yep. So Good night. Should be readable.
This one is MP4, not API, and there's 0 byte, no nothing in here.
Okay, then we need to work until it is. Well, maybe not right now, but
It's okay.
I need
You have to go. Yeah, it's already 8:09. It's too late.
It's too late, but
So I
ask why in his simulation it does work. It shows moving.
So it says mp4.api.
Yes, and it should be non-zero file. I think maybe this version doesn't have.
So when I run it,
Wait. Is what he sent? Is what right sent to you?
yeah,
Ask him to send a version that makes movies.
okay,
With guarantee he has it.
okay,
And then upload and send the link.
okay.
And then you'll keep talking because I don't know what you will decide to do for your PhD study, but if you will interact in some capacity, all students in my group do combine initial and technical.
So I actually am decided. I want to work with computational chemistry.